How do they send gigabits per second through wires like this? Because when you cram bits into the wire that fast, you've got quite a few bits in transit in the wire before it comes out the other end. So it travels through the wire in waves, and this is where it gets interesting. The wire is a bit like a hose, and if I just suck through it normally, no problem. But if I send short pulses through it, it's different. And you can actually hear the sound wave traveling through the hose. It actually bounces off the end of the hose and comes back, and that's how you get that sound. And with high frequencies, wire behaves very similar, just a million times faster. And I got what's left of a big spool of Ethernet wire here. Now I just need something to send pulses down it. And I'll be using this MHO98 1 GHz scope that Rigol sent me for review. And this scope has got a built-in function generator which comes out the back, but I've just set it to a maximum frequency. And the waveform I got here has got a rise time and a fall time of about 8.5 nanoseconds. But I wanted something a little bit sharper, so I programmed this Raspberry Pi Pico to generate very sharp pulses on 4 output lines simultaneously, so I get a little bit more power coming out of it. I just grounded it to my scope, so let's have a look at what comes out. Push auto. And let's zoom in on that. That does not look like a nice pulse coming out of it, does it? And I'm plugging an external monitor into the scope. It'll be easier to film that way. And that just pixel by pixel mirrors what's on the scope screen, so it's not using the full resolution of this monitor. Of course, long leads like this are no good for high frequencies, so I'm going to use the short ground lead on the scope probe and clip that on here. And I'll recapture. And that is much more crisp, but still not great, because my leads are still way too long. So I'm just going to touch the scope lead with the ground on here directly onto the Pico, and what I get is much more crisp. Scope says the rise and fall times are about 700 picoseconds each, but we have a bit of bouncing or ringing, and that's at about 500 megahertz according to the scope, just labeling it with the cursors. Now the probes that this scope comes with are only rated for about 500 megahertz, so that might be affecting things a bit. Now I looked it up, it is possible to get 1 gigahertz scope probes, but they're active probes with active amplifications, and they cost about as much as the whole Rigol scope together for each probe. You need 4. So let's just try it without the scope probes by just putting that on the connector directly. Now the signal is a lot bigger now because the scope probes attenuate by 10 times. And I still get some bounce, but at a lower frequency, and the rise and fall times are actually a little bit slower now, so I might as well go back to the scope probes. I tied the wire plus the scope probe to the Pico and the scope probe to the other end, and not using those long clips, just straight on there. And there's my pulse going in, this is the pulse coming out. We got nothing, so let's zoom out. We're changing the time base. And there's a pulse on the output. So my pulse is 8 nanoseconds long, and it takes it 954 nanoseconds to get from one end of the wire to the other. Looking it up, the propagation for Ethernet wire like that is about 5.7 nanoseconds per meter, so I should have about 167 meters of wire left on that spool. Zooming in on the pulse a bit so we can see it. So that is about half a division wide, and let's scroll over to where the result is. And that is much smaller and way spread out. So let's send something more complicated down the line, this pattern. And we can see there's still remains of our individual pulses, but they're kind of slurred. This needs some signal processing. So I set up a math operator to get the derivative of my output channel, and we got that here. Let's try to declutter the screen a little bit. And we can get even more stuff off of there. And so we see more of a sign of our original pulses here. And I'd like to put some cursors on here, but I keep running into this. The cursors just seem to be disabled. Let's get rid of the math. Cursors are gone. I just cannot get them back. And that, as far as I can tell, is a bug in the scope. And the only way to get the cursors back is to hit the defaults button, but then I lose all my settings. I just changed the code on my Pi Pico so that the signal in yellow that we're sending in repeats at exactly the rate of the propagation delay of the cable. So the line in blue is what comes out basically from the previous iteration, and you can see when the pulse is high it increases, and when it isn't, it kind of settles back. And so then if I use the math function again to get the derivative of that, we can see we have these pulses here, and we have that same pulse pattern here coming out. So without too much signal processing, we can turn this back into bits on the receiving end. And I like that, so I want to save a screenshot, and I just connected the scope to my LAN via Ethernet cable. I could do it wirelessly by plugging into here, but I've already got my wireless mouse thing plugged into here. And now on my computer I can just go to the IP address of the scope, and there we are, and I can do a print screen, take screenshot, and there it is, and I just drag it out and I got it saved. And I can also just control the whole scope like this. So let's start that running again, and you can see it's animating, and let's get rid of the math here. Off. So I can control the whole scope via the web. Except I can't just grab the knobs on the scope to make adjustments, so it can be a bit awkward and frustrating. So if we count each of these things here as a bit, I'm sending 125 million per second. But that doesn't get me to a gigabit per second. But on cables like this, there's 4 pairs and they use all 4. But that only takes me to 500 megabits per second. But gigabit Ethernet actually uses multiple levels of encoding, so they use 8 levels. So you actually have 3 bits for every one of those pulses that I've sent at 125 megahertz, and then they use some fancy error correction, which then gets it down to 1 gigabit and makes it more robust, and that's how they get a gigabit through. But they also have a cleaner signal than I have, because their maximum line length is 100 meters, whereas I sent my signals through 167 meters on my big spool of wire. But what about 2.5 gigabits? Well, they upped the symbol rate to 200 megahertz, which assumes a shorter cable length, and the maximum cable length is shorter and more level, so assuming a cleaner signal, and then you're not necessarily guaranteed to get 2.5 gigabits, just if the cable is good and everything is clean. Sort of like the old 56K modems. Just because your modem was 56K didn't mean you actually got that. I just swapped out my big spool for a 3 meter long piece of twisted pair. Goes down here, comes back up here, and here's what's going in and here's what's coming out. Pretty clean, but if we just scroll to the right a bit, look at how messy that gets. And let's put that on a big monitor. And this is what we get. So it still pops up that correctly, but the main screen is messed up. That's another bug with this scope and this particular monitor. If it powers up with the monitor already plugged in, it messes up, and I just have to deplug it and plug it back in, and then it gets it right. So what is this mess here? It's actually echoes. So let's go back to a simpler pulse. So here we have the pulse, here we have the pulse coming out, then the pulse bounces back to the start, and we pick up a little bit of that coming back, just overpowering the pico, and then we get another reflection here, and then it bounces back, and another reflection. So we have signal bouncing back and forth and back and forth and back and forth. Remember that sound? So if only we had a hose that was infinitely long, there would never be a reflection coming back, because counterintuitively, the sound actually reflects off the open end here, because the wave is much more constrained in the hose than it is out in space, so it's effectively an impedance mismatch. Or maybe we just need something on the end of the hose that looks like an infinitely long hose, something that just kind of perfectly absorbs the sound. And if I just jam this hose into these shavings real good, and I really do need to jam it in there quite deeply, I think there's still a tiny bit of reflection, but much less than there used to be. So I just need an infinitely long spool of wire, and if I put that on the end here, that takes care of the echoes, or at least the echoes are so far away and so attenuated, because this wire does attenuate with the high frequencies, that it's pretty much gone. Yeah, we don't see any reflections coming back. But electrically, the end of this infinitely long wire actually just looks like a 100 ohm resistor. So I just have to put this resistor on the end of the wire, and that for the most part eliminates the echoes. We can still see some stuff coming back on the yellow trace here though. And with a more complex waveform, we can see it would be fairly easy to get those bits back out. But we still have this echo, and we can see a little bit of that echo here as well. And the reason for that is we don't have just 100 ohms here, we also have the scope probe, which is like 13 picofarads. So if I get rid of the scope probe and then put the resistor on here. And we see a tiny bit of reflection here, basically from the other end, which we're not probing because that affects things. So now if I put the scope probe on here, now we see what's on the far end, and we can see now this echo is actually a bit worse when the probe is on versus no probe. But now if I put 130 ohms on the end of that wire, that makes those reflections disappear pretty much completely. And for this long wire, I didn't have echo issues because the high frequency signals get so attenuated by the time it gets to the end and back, it just wasn't a problem. But let's mess things up some other way. So I'm just going to take this wire and coil it up a bit, and as you can see, that doesn't actually affect the signal on here that much. And let's take that coiled up bit and dip it in water. And notice how that delays the signal a little bit and also makes the reflections a tiny bit worse. And that's because the dielectric of the water is rather high, and depending on the dielectric around the wire, that can change how fast the signal travels through it. So dipping it in water delays it and changes the impedance, which changes the reflections, makes it a little bit worse. Okay, let's talk some more about the scope. It may be a 1 gigahertz scope, but I'm not sure how I'm supposed to actually get a 1 gigahertz signal into it. These probes are only rated to go to 500 megahertz, and at 500 megahertz, the input impedance, capacitance-wise, is a similar load as a 50 ohm resistor, so quite high loading. And even if they could go to 1 gigahertz, at that point, at 13 picofarads, that presents like a 12 ohm resistor, like really loading down the circuit. I got the 100 ohm resistor on the output here, and I'm going to probe that with one probe and then both. So here's with one probe, and now adding a second probe, and you can see how that yellow signal gets attenuated quite a lot because of the loading from the probes. But they are very good probes. They do handle very high frequencies much better than my other scope probes. And for high frequency, they come with this spring so that you can have a ground connection right close to the tip. And for labeling, they've got these things for basically marking which trace it is, and this is a rubber band, and I'm constantly pushing these off by accident, so these things are rather useless. I just have to put some yellow tape on this. Now, when dealing with high frequencies, what's often done is just to run it into a 50 ohm cable and into a 50 ohm input on the spectrum analyzer or network analyzer, but this is a high impedance input, and so we just get signal bouncing along the wire. But with the scope, I can set the input to be 50 ohms, and then it properly terminates that wire, so we just get the pulse, although we still get a little bit of squiggles here. And let's just make that a longer pulse, so we basically see this is the rise and we get some kind of echo from that in the cable, which suggests that it's not perfectly terminating to 50 ohm here. There's some kind of different impedance line before it gets to the resistor, or possibly afterwards. And how can I be sure that that squiggle is a reflection of signals bouncing out of the scope? Well, let's just extend the cable a bit. So I probably have some imperfect connectors on the cable too, but this is definitely the bounce coming out of the scope and back. So I'm pretty sure that that 50 ohm termination in the scope is imperfect in that it's not straight at the end of the line. And so how am I supposed to get a 1 gigahertz signal into that scope without distortion? So I think I trust this scope to about 500 megahertz, but beyond that I'm not so sure. But it is nice that it's 4 gigasamples per second because that's shared between channels. And so right now it's sampling at 4 gigasamples per second, but as soon as I turn on a second channel, I'm down to 2 gigasamples because it's shared. So it's nice having the 4 gigasamples because especially as I turn on more of them, now I'm down to 1 gigasample because it's sharing it between the 4. So even if I could get a clean, undistorted 1 gigahertz sample into the scope, I can really only use that with one channel because once I'm at 2 channels, at 2 gigasamples per second, that's not enough to really capture what's going on at a gigahertz. And it's a very sophisticated small scope, but that makes the screen very crowded. I actually kind of prefer the styling on this one, not so much decorations, because you look on here, you have all kinds of extra stuff that doesn't need to be there. Like nice decorative borders around stuff like that, and that just takes up screen space. And this Nercy has got the same size screen, and notice how fast it comes up. And it seems like it has a bigger screen compared to this one, just because there's less crap on the screen compared to here. Of course, this one is not nearly as sophisticated. But thankfully this one's got this button right here, so if you push that, that makes a lot of the clutter disappear. But there's still a gray border around the whole screen, which I find just irritating because that serves no purpose whatsoever other than taking away pixels that should be mine. Oh, there's another irritation. These probes are at 10x only, as in they always attenuate 10 times, which any probe basically you need to turn that on to get full bandwidth. So you have to configure on the scope what the probe gain is so it shows voltages correctly, and by default the probe is 1x even though it only comes with 10x probes, and then if I change the gain on here, I get this huge list of possible probe gains, and I have to kind of find, oh yeah, there's the 10x. So it comes with probes that are 10x only, but to configure it to 10x only, you get this huge list, and it's very unlikely to put anything other than 1x or 10x probes on there. So like, make the 10x and the 1x at least easier to select so you don't have to search for them. And ideally, default it to 10x because that's what it comes with. And being a very sophisticated scope, it takes a long time to boot. Let me show you. So this one's booted. This one's ready. This one takes annoyingly long. And it's ready now. And that one, I'll have to get back to you on that one later. And it's got a lot of knobs on here in a very small space because the scope is small, and that makes these knobs kind of hard to get at. They're just too close together. Although one thing I appreciate is that it's got two separate knobs here, one for each cursor, because on my other scopes, figuring out which cursor you're actually moving has always been annoying. And the touchscreen on this does make various things much easier to get at, more intuitive, although this one being natively a touchscreen interface, it's really quite good that way. I don't miss the fact that this one doesn't have knobs, whereas on this one, if I don't have the knobs, I really miss them. And it's finally booted up. And I can just do finger drags to make adjustments here, although the cursors always seem to jump around when I do that. And I can even zoom in and out with pinch in and out, but this does not scale with how I'm pinching in and out. Basically just going out says, okay, go by one step, and so if I say, oh, I want to double this, I go like this, it's like, whoop, what, where? So it's confusing that way. You have to get used to the fact that the pinch in and out is actually adjusting steps as opposed to working like you'd expect it to. Same thing with vertical, it just jumps by steps. And it's loud. I found the noise from this one quite annoying, but this one ties it. And the reason is this thing consumes an awful lot of power, about 50 watts. And when you look at the back of it, basically there's a big fan here and the back of it is almost entirely heatsink. So it's quite heavy on account of that. And unlike this one, I can't just turn it off because it takes forever to come back on. But it does thankfully have... Oh. Usually when I push the power button, it gives me a choice whether it wants to go into a low power mode or off. I don't know why it just went straight to off this time. And now it's booting back up, and I have to deplug and replug the monitor because that's going to be messed up. And I just acquired this trace, and the nice thing is a long trace buffer, and now I zoom into this, and what's going on here? I have no detail at all here. And the problem is, even though this thing has gigabytes of memory, it defaults to 10,000 points for the trace. So I have to change that, and see, now I can change that to 10 million data points and reacquire. And now I can zoom in and I have lots and lots of detail on here. A frustrating limit of this one is the trace buffer is only 20k data points. So I don't know why this one defaults to 10,000 points when it can do millions. Like this one has 6 million data points you can store, and it basically defaults to maximum. 10k, it's ridiculous, because you acquire the signal and then you want to zoom in and you realize, oh, I forgot to change that setting, and I have to reacquire and then zoom in. And it's a mixed signal oscilloscope because it also has the logic analyzer input, but I haven't played around with that very much at all, because back in the 80s and 90s when circuit boards looked like this, where everything was dip chips and it was slow enough that you could probe it effectively, logic analyzers made a lot of sense. But nowadays, even the little micro that you buy cheaply like this, everything is so fine and the signals are so fast that you really have to be careful that you can actually capture it effectively. So just to put the logic probes on there, how can you even know that you're capturing it correctly if the signals are so fast? That is, if you can get the probes even on there, and the buses are wider and all that, so I don't think logic analyzers are all that useful anymore. Of course, there's still stuff like probing what's going on an I2C serial port, but for serial, 2 scope probes is quite enough. You don't need a logic analyzer. And another cool thing about this one, because it's got the built-in function generator, it can coordinate with that with a scope and do things like a frequency response graph or bode plot. This one is actually for this big spool of wire, and not surprisingly, it has a resonance right at around 235 kilohertz, which is basically a quarter wavelength in the wire. Not surprising that way, because one end is held constrained by the scope and the other one is open-ended. But it's an awfully sophisticated scope, fun to play with, quite the learning curve. But in terms of fewest things that have been done stupidly, I think this is still my favorite. This one is quite good, very capable, but again, it's got some frustrating aspects. But it's still not the only scope I use. I actually use this one, my least sophisticated scope, a fair bit, because this one has no cooling fan. So just to have it going next to the computer monitoring something that I'm debugging is great. And this one is great for just checking things because it comes up really quickly and it runs off of battery, which has the advantage that it does not pick up power supply noise, because this one also runs off a USB power supply. And I found, just double checking what came out of this one produced a much cleaner signal than this one, and that's because I had this plugged into another power supply. And between the power supply feeding into this one and the one feeding into this one, there's a lot of noise. So I ended up running this off of a power bank so that this one also gets as clean a signal as this one did. So running a scope off of battery is actually quite cool. It's not just for when you don't have power. But yeah, back to this one. It's a good scope. I wouldn't trust it to a gigahertz, but for stuff like up to 500 megahertz, great scope. Oh, and I have a YouTube video about every one of these scopes. These two I bought, and these two were given to me.